it away, Dr. Oliveros. And you can share the screen, I think, now.
Oh, yes. That's a good thing. I was looking at my awful photo. That's what I was. It looks like I just woke up at that moment.
There aren't a lot of photos of you on the internet.
I know, I do that
Hard man to find.
in purpose. Well, hello, everybody. So, as already said, my name is Juan Carlos Martinez Oliveros. I am an astronomer. I work in solar physics and in particularly in high energy astrophysics at the Space Sciences Laboratory. I am not from here. I come from Colombia. So my path in science has been long, very long. I study first in Russia, then I study in Australia, and finally I'm here in the United States. So today I'm going to be talking about this mission that I have been working for the last, I think, 2 or 3 years. If one day the slideshow starts. I did practice today and it wasn't, there you go. There you go, it moves. So the mission is called the PADRE, that is, this stands for the Solar Polarization and Directivity X-ray Experiment. This was a mission that was funded by NASA to fly 2025, next year, and it was funded in 2021. This is all, the whole team. I cannot receive credit for any of this because these people are doing the job, not me. I'm just writing reports. That's what my job is about. There are several institutions involved in this mission. One of them is NASA Goddard in Greenbelt. Then you have Southwest Research Institute, CERI, CE Saclay in France. We have also the Fachhochschule in Switzerland, and of course, Berkeley as the lead institution of the mission. So the idea of PADRE is to observe solar flares. So this is a nice movie of the sun where you can see what an explosion in the sun is. A solar flare is just another fancy way to say explosion. And the basic idea is that you have all these magnetic field that is produced in the solar interior, somewhere in a place called, it is believed, that is in the tachocline, that is a region below, very deep in the solar interior. These magnetic fields are produced there, and then they start moving upwards to the surface. Then they cross this photosphere, that is what we can see, and form these loops. From time to time, these loops touch each other, and that's called reconnection. And the magnetic energy that is stored in these loops is being released. And the way that it's released is in the acceleration of particles and hitting the surrounding plasma. That's what we call a flare. There is some material that is going to propagate in our direction, outwards. That is what is called a coronal mass ejection. Those are the ones with the solar wind that produce auroras. And there are other particles that move in the direction of the surface. Those particles are going to interact with the material in there and are going to produce emissions in different wavelengths. The mission that we have is to investigate what is the dominant electron acceleration mechanism in large solar flares. So in other words, we want to understand is how the magnetic energy is stored in the solar corona and how it is converted into kinetic energy. So in that case, the only thing that we can measure with this mission is the degree of beaming. And I will explain that in a few minutes. The degree of beaming of the accelerated electrons in large solar flares. So this is kind of the basic idea. So you have the explosion. Oh, I need a pen. Do I have a pen? Yes, I have a pen. Somewhere in here, you have your flare. It's where the explosion happened. Right? These electrons or particles are injected into a newly reconnected loop here. These particles are then accelerated somehow, nobody knows how, and they're going to move in this direction. As they propagate, because they are in this kind of motion, like spiral motion, they're going to generate microwaves. So you are going to see all these things with a radio telescope on Earth like that. It's an awful radio telescope, but serve the purpose. In another cases, you have that these electrons have so much energy that they are going to heat up the material that is in the chromosphere or in the lower corona. And those are be seen in X-rays. So if you are measuring or detecting these X-rays, then you, in principle, can try to understand how the electrons are propagating. What are the effects of transport? So what is happening to those electrons while they are moving in this loop? Here you have a couple of images taken by an instrument called STIX on Solar Orbiter. That's a mission from the Europeans that goes very close to the sun, not as close as Parker Solar Probe, but it goes close. And this instrument is in X-rays. It can do images in X-rays. So the blue contours in here are the foot points. So these blue things are called the foot points. And the red thing is called the loop top. That is this source here. Let's be clear. All drawings. So these are the foot points, and this is the loop top. So you can clearly see that there is some kind of loop in there. When you see this from Earth, and you map out this image in here, you can see that the contours are really small on the surface, and this is the top of it. So this kind of show you that this picture is kind of correct. The only thing that is missing is to understand how these electrons propagate, how they accelerate. So the big question in solar physics at the moment, in high energy astrophysics, is how is the distribution of these electrons? Is it a beam that is like a tear, or it is a cloud? And the way that we are going to see it is by observing the polarization, for example, or the other one is called directivity. So here you have, this is a fancy map to explain the same. I don't think we should explain it. It's too complicated. So if we want to see is, if we have this hard X-ray flux, is this equivalent to an angular distribution of the electrons? That's kind of the big question. We know that there are some theoretical works that show that this is true. But in that case, what we are going to see is that if a flare accelerated electron is beam, then we need to see, and we should see polarization. And using this polarization, we can deduce this angular distribution. So that means how they are getting into the chromosphere, which angles they are getting into the chromosphere. That defines an instrument that we have that is called SHARP. And I forgot what SHARP stands. I don't know, something polarization. The P is polarization. The other thing that you can do is if you have another spacecraft and you observe the same thing, the same explosion. In that case, you can do something called stereography, because you are seeing from two different vantage points. If you take a look to the difference in fluxes between one spacecraft and the other one, then you can deduce if this is isotropic, it means it's like a cloud, there will be no difference between the two spacecraft. But if it's beam, because like a tear, you will see a difference in this flux, in this emission. So that defines an instrument for us that is called MEDIA. And I also forgot what is the name, what is the acronym means. So why we want to launch this on 2025? The reason is that the sun has something called the solar cycle. So what we know is that there are periods of the great activity, when you see a lot of flares, a lot of sunspots, and another periods where you see none of them. The maximum of the solar cycle at this moment is 2025. It's around here. That's where the prediction says that it is the maximum. So it is the likelihood that we are going to be seeing large flares like the ones that we had several weeks ago that produced the solar storm, are these X-class flares, is higher. That probability is higher. Because our instrument, although in the world of CubeSat is big, in reality our detectors are small. So that means that we need large flares in order to see all of these emissions, all of these things. Our calculation, our prediction is that we are going to see more than 10 of these large flares and about 100 of these small ones. If we delayed by a year our launch, well, the probabilities show that we are going to have less flares and therefore difficult to do science. Right. So this is just a recap. What we are planning to do is just to determine the angular distribution of these accelerated electrons. And we are going to study this using two methods that are complementary and independent. One by measuring the polarization in here, and the other one is by measuring the directivity. That's the way that the spacecraft looks. So many of you probably don't know what a 12U means. A cube of 10 by 10 by 10 centimeters is called a 1U. It's a unit. If you have 12 of those cubes, it's a 12U. So that means that your CubeSat or your satellite is going to be 20 centimeters by 20 centimeters by 30 centimeters, right? 20 in this direction, 20 in this direction, and 30 in that direction. This is the instrument that I was mentioning before for directivity. This is called MEDIA. It is basically a copy of the STIX instrument in Solar Orbiter. The detectors that this instrument has are being produced by CEA-Saclay, that is just the Institute of Atomic Energy of France. That's what it means, CEA. This looks like a small box, like tiny box, like this. All the detectors look like this, and it has 4 of them. So you can see here 4 windows, and so the X-rays will come in this direction. There is going to be a detector somewhere in here. Okay, like that. And then you are going to measure the spectrum of the flares in X-rays. After that, you compare with Solar Orbiter, the emission, and then you can claim that this was a cloud or it was not a cloud. The second instrument, that is the one that we are building in here. Oh, by the way, this thing is tiny. The whole size of it is probably like 4 times this battery. It's tiny. The next instrument, that is this one, that is the one that I'm building, it's huge. That's pretty much the whole satellite. It consists of an scatterer. So the X-rays come in this direction because the idea is that if you have a beam of electrons, they are going to be polarized. It means that when they come here, they scatter in a preferential direction, let's say upward, right? So you need a detector at the top and another detector. So we have 8 detector boards on this. The spacecraft is going to be rotating so that you can check the location, the polarization of the signal that is coming to. The scatter that you have in here is from a material that is called beryllium. It's highly toxic, so we still don't know how we are going to work with it. The detectors that are in here are called Timepeaks 3. They are ASICs that come from CERN, from the Center for Nuclear Research in Switzerland, France, and Germany. The detectors were made for an experiment called the ATLAS experiment in the Large Hadron Collider. So they are designed to measure particles. Yeah. So the timeline that we have, as we said, I'm going too fast, but okay. If you have a lot of questions, that's fine. It started in 2022. We are at this moment in this period. So we are building our mechanical models, our engineering mechanical models. We are testing all the subsystems, all the detectors, everything. We have a review, a NASA review next week on Tuesday. After that, if NASA is super happy with us, that I don't see why they're not going to be, we are going to start building our flight model. This F is flight. These are our detectors that are going to be in space. Our launch date is launch month is supposed to be June 2025, but it seems like it's going to be now October 2025, which I am not happy about, but there's nothing I can do because there are not many rockets. Here you see how staff look at the moment with very happy people. That's something good. Always good to have happy people in the lab. This thing that you see here is our CubeSat structure. That's the structure. What you see here inside is all the avionics. So you have there the batteries, you have the radios, you have the computer, you have the electronic managing system. There are going to be panels on these sides. Those are solar panels, and we are going to deploy panels. The computer looks like this thing in here. Then you have here a simulator for one of our instruments, power supplies. Yeah, so everything is working so far. Medea, that is the instrument that is tiny. For some reason, they decided to build this gigantic chamber to test their detectors. And the basic idea is that they are going to use this source of hard X-rays to learn how to use their Calice detectors inside this chamber. So this is kind of an important thing for us because now we are already testing the thermal properties and how the detectors work. This is our SHARP prototype that flew on a rocket called Foxy. Unfortunately, it didn't work. Well, it did work, but it didn't get any hard X-rays from the sun. But you can see here the detectors. These are the detectors. Those 4 detectors. You can see them in the prototype, how they were bent into the rocket. That's this box in here is the rocket itself. This was launched in April. The day of the eclipse, it was launched to space. And then you have here 2 people working with the prototype, doing some testing of the prototype, clearly unhappy because something is not working. And of course, everything under the watchful eye of Lieutenant Commander Spock. Without Star Trek, there is no space science lab. So this is the summary. I mean, we are going to be expected to be launched in the second quarter of 2025 to a lower orbit. That means that we are going to be between 500 and 600 kilometers height in altitude. we are going to have 2 months of commissioning. That means that the company that is fabricating the spacecraft has 2 months to tell us that everything is fine. Then we have 12 months to do science, and 3 months, I forgot the S in there, to close out, means to finish the mission. So all this work, this 5 years of work, is only for 1 year of glory. Then we are going to be, all our data is going to be public, so you can download it and do as many experiments that you want to do with that data. And I think that's it, because I'm always super fast in my talks.
The perfect amount of time. Thanks, Juan. And we have a question from Liam, who is actually going to work with one of your colleagues, Hunter, this summer on Foxy.
Oh.
So you guys might cross paths. And he asks,
you work on Foxy too, so yeah. So you might have a question about Foxy, but we know you work on many things.
Liam asked, do the solar loops act as an inductor in storing energy? When two loops hit each other, does it cause the magnetic field to collapse, which creates the ejection of particles?
No. So I will try to draw it and explain it. I'm not sure that I'm going to be successful in neither of the two. So you have the sun, the surface like this. There is a region deep in the sun, somewhere here, that is called the tachocline. In the tachocline, there are currents of flow of plasma that moves in the direction of rotation, right? Like, so if this is the tachocline, it spins in this direction, and that generates a current. So the inductor is the current. So these currents are going to generate a magnetic field that is like this, forms a torus around the sun, in the interior of the sun. And then some anisotropies that nobody knows why happens, produce something like an alpha letter, and this thing is your loop, and that moves upwards. I know that there are people that if you have a loop in here, there should be currents, so that's true. It should be like an inductor in that case. But this is an entity that is magnetic in nature. So the currents are present, but they're not supposed to be like that. The flare, there are many cartoons for flares. Let's say that you have the primary loop like this, and then you have a magnetic field line that is open. It goes into interplanetary space. When they touch, for example, in here, the resulting configuration is a tiny loop with a gigantic line. So that's what is happening. So this is called reconnection, because these two lines that have the same magnetic field value reconnect. They touch each other. The energy that is stored around this thing, because this is twisting, is going to be released. So that's where the magnetic field is stored, that twisting. And I'm not sure that I'm explaining this fine.
He said in the chat that he sees and it makes sense. So either Liam is being very kind or you did a great job.
Yeah, he's very kind.
Any other questions for Juan?
Yeah.
Don't see any. I think that means you're ready for your NASA presentation. There'll be no questions from them either.
That's right. Time for the flight readiness review.
No, you know, Link, that is not going to happen like that.
Yeah, I know. They always have to find some stuff to pick on you for, otherwise they don't feel they're doing their job. That's,
No.
that's good. We want them to think critically about everything that people are building, so it's a good thing.
Mhm.
But thank you so much for that very interesting talk, because I love CubeSats, so it's always good to find out more about them. Here at Cinema State, we're building our third CubeSat, and it's supposed to launch for SolarMax as well. So we'll see what happens.
It will work.
And we'll see what happens with the launch schedule.
Oh, the launch
Just
schedule.
like you found out, right, that you can't get lunch till October. They have a lot of trouble finding rides because CubeSats go as auxiliary payloads on, you know, big billion-dollar NASA missions, right? Then they find a little space on the rocket to tuck in a CubeSat. So then you have to sort of
Yeah.
basically, you know, you're waiting for a ride to be arranged for you.
I have a
Yes.
question. Is it the smaller the CubeSat, the easier it is to catch a ride, or the bigger the CubeSat, the more data, so the more likely they are to put you on a rocket?
That's a very good question. I've never actually looked at the CubeSat Launch Initiative statistics.
I don't
My
know.
guess is it's easier to find a ride if you're smaller. But I could be wrong.
I mean, the CubeSat size at the moment needs to be 12U or below for the Cube launch, the launch initiative. I don't think there is a problem with your size. The issue is how, if you pass the test that they need so that you don't make harm to the main payload. If you can't prove it, or you cannot prove that it's not going to hit somebody when it gets into Earth, then you have some issues. So for us, for example, that's an issue because we have tungsten in our CubeSat. And that is highly likely that it's going to get to the surface.
Oh, that it will fall all the way to Earth.
Yeah, well, the heavier elements, you know, don't burn up quite as easily, right? And if you're trying to stop X-rays and hard X-rays, you need to have heavier elements like lead or tungsten. Otherwise, the X-rays or the gamma rays just go right through.
Yeah, so for us, the launch is difficult because we are not supposed to have students in key roles in the development of the CubeSat. But to use the launch initiative, you must have students in key things. So I don't know if they talk each other or they don't, but it seems like
Yeah, probably not as much as we would hope.
Mhm.
All right. Gonna stop our recording.